Well, students, there is one more theorem in the divided difference section. In this lecture, we will finish that theorem and then see an example on the theorem. And then in the remaining time, we will do some exercise problem. Finally, let us also see the following theorem. You are given n plus 1 nodes, x0, x1 up to xn. They are distinct nodes, and you pick up a x in the interval AB such that x is different from any of the nodes that you have chosen. Then you add x to this set. Remember, x is repeated here. Therefore, you have n plus 3 nodes here. Therefore, this divided difference is the n plus second order divided difference, because there are n plus 3 nodes. Well, one node is repeated twice, but still they are considered to be 2 nodes, not as one node. Therefore, it's a n plus second order divided difference. It is a n plus, say, 2 times continuously differentiable function given by this formula. Okay, so if you repeat 2 nodes, then that is equal to the divided difference of order n plus 1, right? And then you consider this as a function of x and differentiate it, and that will be this. Let us prove this part. First, note that by Hermite-Ginocchi formula, the function f of x defined by f of x0, x1 up to xn, x for any x in AB is a well-defined function, and it's also continuous. Now let us consider this term which we want to show in our theorem as d by dx of f of x0, x1 up to xn, x. That can be written as limit h tends to 0, f of x0, x1 up to xn, x, comma, this you write as x plus h. By this, all the nodes are becoming distinct now. And by symmetry, we can write this as, I'm just taking this x to the first position. I'm just permuting it and writing it as limit h tends to 0, f of x, x0, x1 up to xn, x plus h. Note that all these points are distinct. Therefore, you can use the classical definition itself, right? And therefore, this term by Ginocchi formula, you can give a meaning for this. That can be written as limit h tends to 0, f of x0, x1 up to xn, x plus h minus x to xn, right? So this is the classical definition divided by x plus h minus x, and that becomes h here. Now again by symmetry, I will just rewrite this by this. How? I'm just pushing my x to the last position again and writing this as f of x0, x1 up to xn, x, whereas the first one is retained as it is, and I'm writing this expression. Now you can see that this is f of x plus h minus this one is f of x, right, divided by h, and limit h tends to 0, and that is by definition d by dx of f of x, right? And f of x is just for the notation sake we have introduced, and that is nothing but the divided difference of f at the nodes x0, x1 up to xn, x. Therefore, you just got this expression. Therefore, whenever you are finding the divided difference at some nodes where 2 nodes are repeated, anywhere they are, okay? So anywhere they can be, not necessarily at the end, they can be anywhere. Then you can push them to the last term like this, and then start using this theorem to prove that this is nothing but d by dx of f of x0, xn, where x sits anywhere in between. Okay, that's not a problem. So what I'm trying to say is you don't need these repeated nodes to sit at the last two positions. They can be anywhere inside. That's what I'm trying to say. So whenever there are two nodes which are repeated, then they can be written as the derivative of this. Okay. Similarly, you can think of if three nodes are repeated, how we can write. Four nodes are repeated, how we can write. In general, if all the nodes are repeated, then of course we have the formula here. If all the nodes are repeated, you have nth order derivative of x divided by this. Okay, so therefore you should carefully generalize this formula and see what could be if three nodes are repeated, four nodes are repeated, what can be the formula. Let us take an example. Let us consider the function f of x is equal to sine pi x and find the value of the divided difference 1 by 2, 0, 1, 1 by 2. If you carefully see, there are four nodes. Therefore, this is the divided difference of order 3. But in this, there are two nodes which are repeated, right? So you can always write it as f of 0, 1, 1 by 2, 1 by 2, right? And that resembles our previous result, f of x0, x1, x, x. Therefore, we can use the formula proved in the last theorem. Recall from the above theorem, we can write f of 0, 1, x, x as d by dx of f of 0, 1, x, right? And that can be written as d by dx of f of 1, x minus f of 0, 1 divided by x minus 0, and that can be written as d by dx of f of x minus f of 1 divided by x minus 1 minus f of 1 minus f of 0 divided by 1 minus the whole divided by x. Remember, f of x is sine pi x. Therefore, this can be written as d by dx of sine pi x minus sine pi, which is 0, divided by x minus 1 minus, this is sine pi, which is 0, minus sine 0. So the entire term will become 0, and you have a x in the denominator. That also I will take here. And so we have this expression. Now differentiate this and put x is equal to 1 by 2. We will get f of 0, 1, 1 by 2, 1 by 2 is equal to 0. Let us consider this problem. I think this problem is not there in your exercise. Let us take it as an extra problem. In this, we have to use the Lagrange form of interpolating polynomial for a function given by g of x equal to 3x squared plus x plus 1. Using this, you have to express the following rational function as a sum of partial fractions. This is a simple application of Lagrange interpolation form. Let us see how to do this. The idea is to write g in the Lagrange form and then substitute it into the function f of x given above. Now, when we say that we want to write g of x, which is equal to 3x squared plus x plus 1 in the Lagrange form, first we have to know at what nodes do we have to write this g in the Lagrange form, right? First of all, observe that g is a quadratic polynomial. Therefore, if we have to write it in the Lagrange form, we at least need 3 nodes, and let us take these 3 nodes as 1, 2 and 3. Why I am taking this is just you have to take those which are given here. You can see 1, 2, 3 are given in the denominator, that you have to take as the nodes and find the value of g of x at those nodes. So put x equal to 1 in g, you have 3 plus 1 plus 1. So it's 5, and put 2 in g, you will have 12 plus 2, 14, 15, right? And you put 3 in g, you will get 31. Note that when we say that we want to write g in the Lagrange form, basically we are trying to represent the polynomial g with respect to the Lagrange polynomials as basis. Therefore, first we have to find the Lagrange polynomials. For the given nodes, x0 is equal to 1, x1 is equal to 2, and x3 equal to 3. They are given by L0 of x is equal to 1 by 2 into x minus 2 into x minus 3. L1 of x is equal to minus x minus 1, x minus 3, and finally L2 of x is equal to 1 by 2 x minus 1 into x minus 2, right? I'm just writing the Lagrange polynomials. Therefore, we can write the polynomial g of x in the Lagrange form as g of x naught into L naught of x, right, plus g of x1 L1 of x plus g of x2 L2 of x, and that is given by 5 by 2 into x minus 2 into x minus 3 plus g of x1 is 15. Therefore, it is 15 into x minus 1 into x minus 3. Sorry, there is a minus sign here. Therefore, it is minus 15 into x minus 1 into x minus 3 plus 31 divided by 2 into x minus 1 into x minus 2. Now, you just put this g in the numerator because we have taken g to be this polynomial, right? Therefore, you put the Lagrange form for the polynomial g in the numerator. You can write f of x is equal to 3x square plus x plus 1 divided by x minus 1, x minus 2, and x minus 3, and that can be written as 5 by 2 x minus 2 into x minus 3 minus 15 x minus 1 into x minus 3 plus 31 divided by 2 into x minus 1 into x minus 2, the whole divided by x minus 1 into x minus 2 into x minus 3, and that can be written as 5 by 2 into x minus 1 into 1 by x minus 1 minus 15 into 1 by x minus 2 plus 31 by 2 into 1 by x minus 3. So that is the answer for our problem. Next problem is to find the Newton's form of interpolating polynomial for the data given in this table. There are 5 nodes, therefore the polynomial will be of degree 4. To get the coefficients of the polynomial, we will first construct the divided difference table. For that, we have to first write the nodes xi and the function values f of xi in the first and the second column of the table, and they are given by -3, -1, 0, 3, and 5. The corresponding function values are given by -30, -22, -12, 330, and 3458, right? Let us first construct the divided difference of order 1, which I generally represent like this, where you have the first dot for the first argument and the second dot for the second argument. So that's given by, remember, you have to write it in between these two numbers, right? So that is given by 4, and in between these two numbers, you have to write the value of f of x2, x1. Remember, this is f of x0, x1, right? Similarly, we have f of x1, x2 as 10. Similarly, f of x2, x3 is 114. I leave it to you to compute that. It's very simple. And finally, we have f of x3, x4 is given by 1564. Let's go to the column for the second order divided differences, and we have f of x0, x1, x2 written in between these two numbers, and that is given by 2. And similarly, we have to write the next divided difference in between these two numbers, and that is given by 26. And finally, the last entry is 290. Now let us write the divided difference of order 3, and that is given by 4 and 44. You have to write the first entry in between these two and the second entry between these. And finally, the divided difference of order 4 has only one entry in the table, and that is written between these two numbers, and that is given by 5. Now remember, the Newton's form of interpolation for the given data is given by the formula f of x0, the 0th order divided difference, which is nothing but f of x0 plus f of x0, x1, right, into x minus x0 plus f of x0, x1, x2 into x minus x0 into x minus x1 plus f of x0, x1, x2, x3 into x minus x0, x minus x1 into x minus x2 plus the last term given by f of x0, x1, x2, x3, x4 into x minus x0, x minus x1, x minus x2, and x minus x3, right? Where x0, x1, x2, x3, and x4 are given as -3, -1, 0, 3, and 5 respectively. And what are these numbers? this is nothing but your f of x naught, and this is your f of x naught comma x1, and this is f of x naught, x1, x2. This is your f of x naught, x1, x2, x3, and finally this is f of x naught, x1, x2, x3, and x4, right? You simply substitute all these values in the right hand side expression. You have minus 30 plus 4 into x plus 3 plus 2 into x plus 3 into x plus 1 plus 4 into x plus 3 into x plus 1 into x plus 5 into x plus 3, x plus 1, x, and x minus 3, right? You can either leave it here or you can simplify it from the examination point of view. But if you prefer to simplify it, it gives you a 5 into x power 4 plus 9 into x cube minus 27 into x square plus minus 21x minus 12. And that is the answer. So if I ask you to construct the Newton's form of interpolating polynomial for a given data, you have to construct the divided difference table. There will be some weightage for this also. On the other hand, if you directly compute these coefficients, then those partial marks you may be losing. So better if when I ask you Newton's form of interpolating polynomial, you construct the divided difference table, and from there you circle like this those entries which you are taking into your polynomial, and then you go to compute the polynomial. Next, let us compute the nth divided difference f of x naught, x1 up to xn for the function f of x equal to 1 by x. Let us compute this by induction. Let us consider the case when n is equal to 0. In this case, we have f of x naught is simply equal to 1 by x naught, right? Let us now go to compute for n equal to 1. We have f of x naught comma x1 is equal to f of x1 minus f of x naught divided by x1 minus x naught. Recall that this is nothing but f of the 0th order divided difference with node x1 minus the 0th order divided difference with node x naught divided by x1 minus x naught, right? And that is going to be 1 by x1 minus 1 by x naught divided by x1 minus x naught. Upon simplification, we can write this as x naught minus x1 divided by x naught into x1 into x1 minus x naught, right? Therefore, f of x naught comma x1 is equal to minus 1 by x naught into x1. Now let us go to find the divided difference for n is equal to 2. So basically what we are doing is we are computing for few values of n, and from there we are trying to guess the general form of the divided difference for a general n, and then we will try to prove it by induction. That's all. So we will go for few n's and then guess the general form from there. So let us do it for n is equal to 2. In this case, we have f of x1, x2 minus f of x naught, x1 divided by x2 minus x naught, right? but we know what is f of x1 comma x2, that is minus 1 by x1 x2 minus of minus, therefore it's plus 1 by x0 x1 divided by x2 minus x0, and that can be written as minus x0 plus x2 divided by x0 x1 x2 into x2 minus x0, and that is equal to 1 by x0 x1 x2. From here we can guess the general form. So let us assume that for a given k greater than 0, we have f of x0 x1 up to xk is equal to minus 1 to the power of k divided by x0 x1 up to xk. We are only proposing this form. We have to prove this. Well, that proof can be done by induction. So we assume this form for k and prove this form for k plus 1. By definition, we have f of x0 x1 xk comma xk plus 1 is equal to f of x1 x2 up to xk plus 1 minus f of x0 x1 up to xk divided by xk plus 1 minus x0, right? That is equal to, now observe that this is a divided difference of order k, and this is also a divided difference of order k, and we have assumed that these two terms are given by this expression. Therefore, we will simply substitute this expression for these two terms. We get minus 1 to the power of k divided by, the nodes are x1, x2 up to xk plus 1. Therefore, we have x1, x2 up to xk plus 1 minus, similarly here we have minus 1 to the power of k divided by, the nodes are x0, x1 up to xk, and then divided by xk plus 1 minus x0, right? Now you can just simplify this to get the same with minus 1 to the power of, now k plus 1, you can just simplify it and check. You will get this x0, x1 up to xk plus 1. So that completes the induction, and therefore the required expression for the divided difference is given by this. Therefore, f of x0, x1 up to xn is given by minus 1 to the power of n divided by x0, x1 up to xn. So that's the answer.